One of the most common software vulnerabilities in computer programs is known as the buffer overflow. A buffer is simply a location in a computer's memory that can hold data, but if you don't check carefully how much data it can hold and to make sure that you don't put more data in there than it can hold, you can have a problem. And why is that? Well, first off, let's start saying that this is a vulnerability that we typically see in programs written in C. C is still a very popular programming language, widely used, especially when it comes to software that needs performance, that needs to be efficient. So just about any operating system, for example, operating system driver or any older information system is most likely still written in C. So there are many systems out there to which these vulnerabilities still apply. The downfall is that the people who developed C assumed that programmers knew what they were doing. And that's not always the case. Programmers are people, people make mistakes. And that means that sometimes we have a situation where we might, for example, take user input and don't check that user input appropriately before we're doing something with it. And so I might have a buffer that can hold 80 characters, but instead I'm trying to stuff 100 characters in there, and that does not work. If we know that most operating systems are still written in C, and that C in particular is susceptible to these types of errors, we see that that's a problem because a vulnerability in an operating system can typically give significant access to data and processes running on a computer. So we want to avoid these buffer overflow vulnerabilities as much as we can. There are several other software vulnerabilities, programming mistakes that are closely related to buffer overflows, and we'll explore a few in this lesson. First, let me get a couple of terms out of the way. The source code is the computer program, but then as it is intended for the human consumption, the programmer. Computers don't need programming languages to be readable and writable, but people do. So the source code is meant for programmers. Eventually, when we are done with our source code, we try to translate it to a format that is optimized for use by the machine. Typically, we do that through a compiler. And now we have a program. I can compile or interpret multiple programs from the same source code. And last, we have a process, and that happens when you run a program. So a running program is called a process. A compiled source code is called a program.
Let's take a look at a very simple C program. We're going to start with including some system headers. All C programs must start with the main function, which argv array looks like this. A C program must return 0 on successful completion, and in this case we'll just go hello world, new line, and then we'll call a new function called fill. Fill is not going to return anything. It also is not going to take any input, but it is going to define a buffer of, say, I don't know, 50 characters. And we're going to say in that buffer, what is your name? And we're going to read from that buffer. Read from standard input, put it in the buffer, and we'll go hello, and then your name. So that should be a simple program that runs. Save and run. Except that I made a typo here. I should have said .h. And now we run. Now when I run this program, it's printing hello world, including a warning, and the warning is exactly what we're getting at, so let's ignore that for now. And it's asking for my name, and it prints it back to me. This is exactly what we expected to see when we looked at the program itself, when we looked and said, hey, we started by printing hello world, then we call the function prints what's your name, it reads what I type in, and then echoes it back to me. Now this is 50 character buffer. So let's run this again. and go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Copy. 20, 30, 40, 50, 5, 6, 7. So 55. This still works, but if I keep on extending my input, the program aborts. And why is that? That's exactly what the root cause of this vulnerability is. So let's go explore that a bit more. Okay, let's go take a look and see what really happens when we run through this program. On line 13, we just print hello world. Not terribly exciting. And then we call foo, which is the function defined in lines 3 through 10. When foo is done, we expect it to execute line 15, which is return 0. But the question is, how does the compiler know that when foo is done, it needs to continue at line 15 and not say at line 16 or at line 2 or whatever it may be? It needs to keep track of that somehow and somewhere. When a program executes, it creates what's called a stack frame. It's a location in memory where it keeps track of variables and other important things. The stack is a traditional stack data structure, like you've learned about that in other classes, which basically means the first things to come out is the last thing to go in. So it's last in, first out. And the first thing that happens when I call a function is that somewhere the first thing on the stack is going to be the return address. And basically what that return address is a memory location, a physical address that contains the next instruction to execute. Since we are dealing with a 64-bit operating system, that is 8 bytes right there. And then it starts adding to that stack any command line arguments that may have been passed into this function. In our case, foo has no argument, so that's easy. And next, we define the first local variable, which in our case is buff. In C, a character is 1 byte long, so I have 50 bytes worth of storage here. And in those 50 bytes, I can start accumulating my string. Remember, C strings are null terminated, which means that I can hold 49 characters plus the null character to signify the end of the string. Now, what happens is that it starts filling in my buffer from top left this way. And that means that if I keep on adding to my buffer all the way till here, and I go over this boundary, what I'm doing is overwriting this return address with whatever values I've just put in. C is one of those programming languages that does not do boundary checking, so it's more than happy to do that for you. And that basically means this: if I take an input, which I do in my program on line 7, and I don't do anything with it, I don't make sure, for example, that that input isn't more than 49 characters long, as an attacker, I have a way to inject machine executable code into my program. And what I'm going to do is, at least initially, put in some 50 characters worth of garbage just to over and fill up the buffer. And then another 8 bytes with the memory address that I want the program to execute next, not necessarily that the programmer wants to execute it. So I'm overwriting the return address in the stack. And that is your basic concept of a stack overflow attack. I'm going to fill up my buffer to the point that I overwrite the return address with a location that I want to execute, be that another function in the program or a reference to memory that I provided, doesn't really matter. I can control the execution of that program at that time. we are filling up our buffer. I know that I want to end my buffer here in the last 8 bytes with the return address of the code that I want to execute. Now the question is, what does this buffer look like? And where do I find the code that I want to execute? Well, remember, I just have a whole bunch of space here that I completely control. That is the input that I provided. So while I initially might just put some stuff in there to see if it works and if I can crash the program, at a later stage I probably want to have some form of a machine executable payload in my buffer overflow. And then the machine executable payload is probably padded with some stuff on the front and some stuff on the back. Now, if I can then figure out what the execution address is here of that first byte of machine executable payload, I can overwrite my 8 bytes of the return pointer, which signifies the next command that will be executed, with the start of the payload that I provided. In reality, we do it a little bit different. We typically start with something called a NOP sled. The NOP sled is a special Intel command, hex 90, which is a command that says to the processor, don't do anything. But it's a valid command, and if I have a bunch of those in memory and I can inspect my memory, I can recognize where I am. It also doesn't matter exactly where on this NOP sled I'm going to land, because it's just going to execute and do nothing again, until it hits my payload. So my NOP sled typically goes in front of my payload. What we see very commonly in exploit development is that we're running the stuff in a debugger and we want to be able to visually recognize. And that means that we want to probably put in some recognizable pattern in here, that if we look at a raw dump of the memory in my exploit, I immediately recognize that as not just a random pattern, but as something that was particularly crafted. So I'm going to make that pattern all hex 41s, or whatever it may be. Hex 41 is the uppercase A, followed by my NOP sled, followed by my machine executable payload, and then followed by some padding enough to get to the area in my bytes. And that means that at this point, if I have a 50 byte buffer, I have 50 bytes worth of machine executable payload that I could work with. And that's the basic concept of a Stack Overflow exploit development.